In this video, I am going to discuss mass spectrometers. In the next video, I will talk about the fragmentation and how to read the mass spectra. But in this one, I am going to discuss at least a few of the methods by which mass spectrometers work. And so mass spectrometry provides information on the molecular weight and molecular formula of our molecules that we are looking at. It only requires a very small amount of sample, and as we'll see in future videos, it works very well in complement with NMR and IR spectroscopy. So there are essentially three steps to the mass spectrometer, and I will go through each of them in turn. So the first one is the ionization. So this is actually going to create the ions. So it turns the sample into positively charged ions of different fragment sizes. So then the next step is ion sorting. So that's separating these ions based on their mass. And then there is detection. And so that is to detect the ions. And we want to do that based on the mass because we want to see what different fragments that we end up with. So we want to be able to tell them apart based on their mass. So the first step, as I said, is the ionization. And so ions are produced that are positively charged. And in most cases, they are going to be just a +1 charge, which are often denoted with Q or Z. So you'll see it in both ways. I mostly use Z, but you will often see it as Q as well. And so the ions produced are just fragments of the entire molecule. So we have the M plus here, which is called the molecular ion, and that is the mass of the entire molecule. Well, usually sans like a single electron, but those have such small amounts of mass that it doesn't make that much of a difference. And then you also get fragments that are smaller than that. So separation, which we'll discuss here in a little bit, is based on the ratio of mass to charge. And since the charge is usually just +1, we are looking at essentially a separation based on just the mass. And so that's what we're trying to do here in the mass spectrometer. And the ionization is the step that actually splits these molecules into fragments that have the positive charge. And so there are two different types of ionization. There's what's called the hard ionization, which just uses a lot more energy and creates a lot more fragments. And so the one we'll be looking at for this is the commonly used one called electron ionization. And then there is soft ionization, which creates fewer fragments. And the ones we'll be looking at for that are the electrospray ionization and the matrix-assisted laser desorption ionization, usually shortened to MALDI. So electron ionization, so this is a very common use because this, as I said, generates a lot of fragments. The electrons are produced through what's called thermionic emission, so it's essentially, you can think of like a filament on an incandescent light bulb that's throwing off electrons. And so we can accelerate these electrons to 70 electron volts of energy. And so we do that in the region between the filament and the entrance to the ion source block. So the sample under investigation is exposed to the ion source perpendicular to the orientation of the electron beam. So that looks kind of like this. This is our molecule here. It's sent through this thing. We have these electrons moving down this way. They collide with the molecule and they will knock off electrons like this. And so one electron will knock off another electron, which is why we end up with two here. And so then our sample becomes positively charged, and it can fragment into smaller pieces, or it can go on to just be the entire thing but with a positive charge, and that's called the molecular ion. And so the radical cation products are then directed towards the mass analyzer by a repeller electrode, and the ionization process often follows predictable cleavage, which is the thing that I will be talking about in the next video. And that has to do with the stability of the different types of fragments you can get. So the amount of the different types of fragments is based on the stability of those fragments. So over here, this is kind of what I'm talking about. So we have an electron, we have our molecule here, we run into it, it knocks off an electron, so we end up with two electrons. And then we have this here, which is what's called a radical cation. So if we did that with methane, for instance, it would look like this. So one of these bonds between the carbon and hydrogen is made with just an unpaired electron. And so it has that radical electron and it is positively charged. And so that would be our molecular ion right here. And as we'll see in the next video, you can break off larger chunks of larger molecules, and those are the fragments that we will be looking at. And so the potential of the anode, so this is called the electron trap, and this is in our ionization chamber here. It looks kind of like this. So we have the electron trap right here. This is our filament. The electrons are moving this way, where our sample is being repelled by this repeller here so that it goes this way. So those are perpendicular to each other, and the ions, the fragments, are accelerated out here into the separator, which is the next thing I'll talk about after talking about the ionizers. And so to increase the ionization process, we have a weak magnetic field. And so because of this, the electrons travel in a narrow helical path. So we have a magnetic field often that's going in this direction. And so the ions are actually going in a sort of helical path through here. And so that can increase the time of flight. So the positive ions that are generated are accelerated by the repeller electrode. So that's this right here, into the accelerating region through the slit in the source block. So out here will be our accelerating region, where we accelerate these into the separation part of the instrument. So by applying a potential to the ion source and maintaining the exit slit at ground potential, so we have a potential that's going down in this direction, ions enter the mass analyzer with a fixed kinetic energy. And so that is the electron ionization. Another popular one is this MALDI here. So ionization is initiated by irradiation of the sample with a laser beam. And so the sample is in a matrix of organic molecules, which is used to help protect the molecule or analyte from the irradiation and to facilitate vaporization and ionization by absorbing the laser irradiation. So what that means is we have our sample here. So the blue dots here are like our matrix molecules, and the red is the analyte. We hit it with a laser beam, and it causes these to sort of come off of this sample here and go into our mass analyzer. So these matrix molecules, so this is a list of common ones that I got from Wikipedia right here. So a lot of these have the cinnamic backbone in it, and so that looks like this right here. And so these are a lot of the matrix molecules that we can use here. And so there isn't really an agreed upon model of what's actually happening when the laser beam hits it. So there is what's called the gas phase protonation model and the lucky survivor model. This just has to do with how protons and electrons are sort of being exchanged between the matrix and the analyte. And so you could go down a deep rabbit hole into these models about how this is actually happening, but what really matters for our purposes here is that we get this mixture of the analyte and the matrix right here when we are doing this MALDI ionization. So the solvents evaporate, leaving matrix with analyte spread throughout the crystals in a MALDI spot. The applied laser pulse vaporizes the matrix containing the analyte, thus creating ions which can be extracted by a high voltage and passed to a mass analyzer. So the laser irradiation can be applied to the spot either in a vacuum or at atmospheric pressure. So that would be AP MALDI. And so this is the spot right here that they're talking about. And so we hit it with the laser beam right here, and that causes the ionization. And the laser beam is usually UV, so ultraviolet. And so then there is the electrospray ionization. This is often used for larger molecules such as proteins, and it often produces ions with greater than +1 charge. And so you can use that for getting different masses and therefore expanding the mass range. But this also doesn't create that much fragmentation. What you often see, especially if you do mass spectrometry and biochemistry, is this is done with what's called tandem mass spec, or just MS, which I'll discuss later on in this video. And so those were the three types of ionization I wanted to talk about. The next step is the ion sorting. And so there are multiple ways of doing this as well. One of the ones that usually gets discussed when talking about this is what's called deflection by magnetic fields, or sector analysis. And so what we're doing is we have the ionization going on over here. Our particles, which is these dots here, go through this magnetic field right here, which bends them based on their mass and charge. And so then they come through and go to the detector. And the magnet has a variable strength. And so you can just select for the mass of fragments that you want coming through. So deflection by an electric and magnetic field, this was initially the predominant way to analyze ions in mass spectrometry. So the deflection of the ion of charge Q, or we can call it Z, of mass M by an electric and magnetic field depends on the M over Q, or M over Z here. And so if we think about our physics, so we have this magnetic field, and this is going into the screen. That's what these little crosses are telling us. And we have our particle here. So this is our positively charged particle. It has some velocity in this direction, and the magnetic field will apply a force in this direction. And so we are bending this, and that bending, the amount of force that's going to be applied, is based on the mass and the velocity here. So if these all have the same velocity, then the amount that they bend is going to be based just on the mass and the strength of the magnetic field. And so we have it so that we can adjust the magnetic field strength and then have the particles with a particular mass actually make it through the bend here, where any other ones will not bend enough. They'll hit there, or they'll bend too much and hit right there. And only the ones with the mass of a certain amount will actually make it through. And then we can adjust the strength of that magnetic field so that we can actually determine what the mass of the particles that are making it through actually are. And so it looks kind of like this. So again, we have our ion source here, we have the ion accelerator, we have the ionization filament right here, and so the particles go into the magnetic field here, and then based on the mass, because they're all going to have a Q or Z of +1, it's based on the mass how much they will actually bend. Then we can have some detectors here, so this calls them Faraday collectors. That's one type of detector that you can use. There are other types as well that I will briefly discuss below. But anyway, this is the sector analysis type of mass spectrometry. So another popular one is what's called time of flight. And so it's just based on how long they are actually moving. So ions with different mass can have different transit times when passing through a drift region of a mass spectrometer. So this is called, as I said, the time of flight, or TOF, or sometimes called TOF instrument. Usually uses the MALDI, and so after a laser pulse and extraction of the ions by the electric field E1, it gets sent into another electric field, which we'll call E2, which accelerates the ions into the drift region with some energy QV, where Q is the ion charge and V is the applied voltage. And D is going to be our distance traveled right here. What this means is that any particle with the same mass and charge will be accelerated by the same amount, because the kinetic energy of the ions is 1/2 mv squared equals QV, where again Q is our charge, V is our voltage. And so the velocity of the particle is this right here when we solve for the velocity. So we see we have the charge and the mass here, so you can probably see where that's going. So if L is the length of the drift tube, the transit time will be this. So we just do L divided by our velocity here. And so we end up getting this right here, where we see that this is proportional to M over Z, where remember Q and Z are kind of the same thing. And so again, we can get this M over Z here, which is the thing that we are interested in. And so these TOF instruments often include what's called a reflectron, where a series of charged rings or grids act as an ion mirror, and this increases the path length L in order to obtain better resolution. So what we have here, so again, we're using MALDI, we hit it with the UV laser, it ionizes, we have this acceleration zone. And so the amount that each particle is accelerated will be based on their mass, as we saw above. So the time of flight is going to be based on the mass, as we saw here. And so they're accelerated. And then we want a large time of flight zone, because the longer they're in the time of flight zone, the more they're going to separate, because they're going to have this small difference in their velocity. And so as you allow it to travel for a long time with these small differences in velocity, you're going to get more separation. So that's why we often have these reflectrons here, because we want to have this whole time of flight right here, but then we want to add even more time of flight right here. And so the more time of flight you can actually get on this, the more separation you will get. So another type is called the quadrupole analyzer. And so that uses 4 of these rods here, which will have differences in the electricity going through them. So we see the quadrupole consists of our 4 parallel metal rods. Each opposing rod pair is connected together electrically, and a radio frequency voltage with a direct current offset voltage is applied between one pair of rods and the other. So ions travel down the quadrupole between the rods. Only ions with a certain mass to charge ratio will reach the detector for a given ratio of voltages. Other ions have unstable trajectories and will collide with the rods. This permits selection of an ion with a particular M over Z, or allows the operator to scan for a range of M over Z values by continuously varying the applied voltage. So we can see that in this image right here. We have this red one here, which has the correct mass over charge. The blue one does not, and so that just kind of gets thrown off. And we can see that with this one over here as well. So we have these ones making it through here, where these other ones are sort of getting thrown off. And that's based on the mass and charge of those particles and the amount of electricity we are actually sending through these quadrupole rods here. So we can see this shows this one and this one as positive, this one and this one as negative. And so we have the ones sort of on corners from each other as going in different directions. Then we also have what's called ion trap mass spec. And so we have a chamber that looks like this. And so the ions produced in the source of the instrument enter into the trap through the inlet and are trapped through action by the 3 hyperbolic electrodes. So that are these blue things here, the ring electrode and the entrance and exit end cap electrodes as well. So we have the entrance end cap and exit end cap electrodes right here. Various voltages are applied to these electrodes, which result in the formation of a cavity in which ions are trapped. The ring electrode radio frequency potential, which is an AC potential of constant frequency but variable amplitude, produces a 3D quadrupolar potential field within the trap. This traps the ions in a stable oscillating trajectory. So the ions are inside this thing in an oscillating trajectory, essentially just spinning around in a circle inside of there. So the exact motion of the ions is dependent on the voltages applied and their individual mass to charge ratio. So again, that's the thing we're always looking for here in our mass spec, is the mass to charge ratio. For detection of the ions, the potentials are altered to destabilize the ions, resulting in their ejection through the exit end cap. the ions are usually ejected in order of increasing mass by a gradual change in the potentials. The stream of ions is focused onto the detector of the instrument to produce the mass spectrum. So you can essentially think of the ions inside here as sort of spinning around in a circle. They are adjusting the potential within here, and so some of those ions, based on their mass, will get sent flying out of here at different times, well, at different voltages, at different potentials based on their mass, where the potential is changing in time. And so that is the ion trap mass spec. There is also the Fourier-transform ion cyclotron resonance. So in this one, the ions are trapped in what's called a penning trap. It's somewhat similar to the ion trap above. So we have our ions inside this trap here, and they are, again, spinning around. So that's kind of what this is showing right here. We have this positive charge here that's inside spinning around, where they are excited at their resonant cyclotron frequencies to a larger cyclotron radius by an oscillating electric field orthogonal to the magnetic field. After the excitation field is removed, the ions are rotating at their cyclotron frequency in phase, so as a packet of ions. These ions induce a charge, so detected as an image current, on a pair of electrodes as the packets of ions pass close to them. So that's what is showing on here. So we have these plates here. As the ions spin around inside of this thing, they are inducing electric currents in those plates. And so that induces an electric current here in these wires here, which then will have a certain frequency that we can then detect in the time domain signal here. The resulting signal is called a free induction decay transient or interferogram that consists of a superposition of sine waves. So as I said, this is going to induce a current that will then have this frequency here. And so it's going to be some complex frequency that we then use a Fourier transform to decompose. And those different frequencies are going to be based on the size and charge of the ions that are inside of it. So the useful signal is extracted from this data, again, by performing a Fourier transform. So the cyclotron frequency here, omega sub c, is related to the mass and charge by this right here, and to the strength of the perpendicular magnetic field. And so again, we have a magnetic field here, which remember is going to cause a inward force that's going to cause our particle to move in a circle. So the ions are trapped and oscillate at a low incoherent amplitude here. So we then excite the ions and induce the potentials on plates at resonance frequency. So we have our plates here, we're inducing those potentials that then send an electrical signal through the wires here that we can then detect. And so then the induced potentials are picked up by a preamplifier and digitizer, so something like this. And so we can look at the electric signals that are made by the movement of those ions past those plates. All right, so tandem mass spec. So this isn't like a new type of way. It's essentially just combining ways that I've already talked about. So the molecules of a given sample are ionized, and the first spectrometer, which they call MS1, separates these ions by their mass to charge ratio. So a lot of times this will use that electron spray ionization here, which doesn't have as much fragmentation. But the ions of a particular M/Z ratio coming from the MS1 are selected and then made to split into smaller fragment ions. So we put it into another mass spec essentially that then uses a stronger type of fragmentation to break up those particles of a certain size into yet smaller particles, into yet smaller fragments, so that we can then detect those. And so we can then sort of focus in on a particular mass and then break it into smaller masses within that, so that we can see the molecules at a higher resolution. You can maybe see how this would be really nice for very large molecules such as proteins. All right, so then the last thing I wanted to talk about, and I'm not going to spend as much time on this because it's kind of not that relevant for an organic chemistry class, but we do have detectors. So we do have to detect these fragments based on their charge and mass. So typically some type of electron multiplier is used, though other detectors such as the Faraday cups and ion to photon detectors can also be used. And so these are all things that just detect charged particles. But because the number of ions leaving a mass analyzer at a particular instant is typically quite small, considerable amplification is often necessary to get a signal. And so they often use these microchannel plate detectors. And so those look kind of like this. So what happens is our ion comes in here, it will start running into the sides of this, and that will actually start breaking off more electrons so that we amplify our signal. And so that will look kind of like this, where we have right here our microchannel plate, but we are still going to use some sort of electron to photon type thing going on here, or a CCD like this. And so that is how we do the detection on these. There is obviously a lot more I could talk about with detectors. You could probably take an entire semester course just on any one of these type of things, but that was all I wanted to talk about in this video. I hope you found this helpful, and I will see you in the next one.